Physics for Philosophers, An Introduction. Chapter 2 Section 5. Time and Space in Classical Mechanics. The problem of time and space, which we will consider in this section, boils down to the question of whether time and space are absolute or relative. This question can be understood twofold. In the approach typical of physics, absoluteness is understood as invariance with respect to the choice of the frame of reference. Absolute time is the same in every frame of reference, while relative time varies depending on the frame in which it is measured. The same applies to space. On the other hand, the second understanding of the dispute of absolutism versus relativism, also known as relationalism, is more philosophical in nature. This is a question about the ontological nature of time and space, whether they are separate entities, independent of other substances, or whether they are secondary in nature, depending, for example, on the existence and properties of material objects. The absolute character of time and space in the first sense does not yet guarantee absoluteness in the second sense. It may be that in every frame both time and space look the same, but ontologically they are dependent on some other entities. On the other hand, the dependence of time and space on the choice of a frame of reference seems to deprive them of the character of ontologically separate entities. It is relatively easy to answer the question whether according to classical mechanics, time depends on the frame of reference. Due to the assumed Galilean transformation, time is measured equally in all systems and is therefore absolute in the physical sense. However, the status of space is not obvious. The Galilean transformation changes the value of spatial coordinates, but does this mean that space itself also changes from system to system? It depends on what exactly we mean by space. In the context of physical considerations, we can naturally identify space with a distance function defined on a set of points. A space is called invariant if the spatial distances between points or events are the same in every frame of reference. Let us investigate this matter further. Let there be two events A1 and A2 with the coordinates x1, t1, and x2, t2. For simplicity, we omit the other two spatial coordinates y and z. You can always choose a coordinate system in which the y and z coordinates of both events are 0. The spatial distance between A1 and A2 is, of course, x1 minus x2. However, when we apply the Galilean transformation, this distance will typically change. The spatial distance between two events is not generally invariant with respect to the change of the frame of reference. This can be illustrated with a simple example. Imagine a passenger sitting on a train and drumming his fingers on a table. Two consecutive finger taps in the train system have 0 spatial distance, while from the point of view of an observer standing on the ground, their distance is equal to the distance traveled by the train in time between the finger taps. Note, however, that the distance in one frame will be equal to the distance in another, as long as the time coordinates of the events A1 and A2 are the same. This shows that the distance between simultaneous events is an invariant of the Galilean transformation, in fact, any coordinate transformation connecting two arbitrarily moving systems. Thus, space can be considered invariant with respect to the choice of reference frame, if space is defined by all spatial distances taken at the very same moment. The set of all events, points, occurring at the same moment and connected by the distance function is called instantaneous space, snapshot, or momentary space. From our analysis, we conclude that instantaneous space is an invariant of the Galilean transformation, and therefore it is absolute in the physical sense. On the other hand, the temporarily extended, global, space, including objects lasting in time, is not absolute, because its characteristics by means of the distance function depend on the choice of the reference frame. The above considerations can be illustrated with the help of space-time diagrams. Such diagrams take into account spatial axes and one temporal axis on which we mark the time coordinate of a given object or event. For obvious reasons, we cannot graphically represent the general case of 3 spatial axes and 1 temporal axis, so we usually reduce the number of spatial axes to 2, and sometimes even to 1 x-axis. The diagram shows an oblique line that represents the path of a body moving at a constant velocity relative to a given system. This line can also represent the temporal axis of a new reference frame, primed, which is in motion with respect to the original frame, unprimed. The time axis connects events that in a given system have all spatial coordinates equal to 0, they occur at the origin of the system, and the origin of the primed system moves relative to the unprimed one. Horizontal planes represent instantaneous spaces that remain the same in any frame of reference. On the other hand, the lack of a global space is revealed in the fact that it is not possible to absolutely connect points belonging to different planes by the relation of being in the same place. Two non-simultaneous events that occur in the same place with respect to one frame of reference do not occur in the same place according to another frame. In other words, the concept of the same place is relativized to the frame of reference. The interrelated concepts of motion, rest, and same location turn out to be only relative, not absolute. Let us now move on to the philosophical issue. What is time or space, really? Should we imagine space as a kind of empty container filled with places ready to receive physical objects? Is time an extension made up of entities, moments, that follow one another, even when nothing is happening in them? In order to present this issue more clearly, we can make use of a concept taken from Aristotle, namely that of a substance. In Aristotle's approach, a substance is a being capable of independent existence, i.e. one that is not dependent on other beings for its existence. For example, concrete physical objects, stones or trees, are substances, but their properties are not. We may therefore ask whether time and space are substances in the above-mentioned sense. Would space exist if there were no objects filling it? Can time exist without events occurring in it? An affirmative answer to the above questions is given in the position of absolutism, also called, for obvious reasons, substantivalism. Newton himself was an ardent supporter of philosophical absolutism in relation to time and space. Widely known and quoted excerpts from his Principia leave no doubt about it. Absolute, true, and mathematical time, of itself, and from its own nature, flows equably without relation to anything external, and by another name is called duration. Absolute space, in its own nature, without relation to anything external, remains always similar and immovable. Place is a part of space which a body takes up, and is according to the space, either absolute or relative. Absolute motion is the translation of a body from one absolute place into another. Note that Newton links the position of absolutism in the philosophical sense with its physical interpretation, maintaining that there is an absolute concept of place, motion, and rest independent of the state of motion of the observer. Newton did not yet use the concept of a frame of reference. The founder of classical mechanics presented theological arguments for his position, but his most famous argument refers to a physical experiment. This is the famous bucket argument. Imagine a bucket filled with water and hung on a rope. The rope is twisted and then released, resulting in the bucket starting to rotate. In the first phase of movement, the bucket rotates, while the water remains at rest due to its inertia. When observing the surface of the water, we do not notice any effect, the surface is flat. The water then begins to take over the rotational motion of the bucket, resulting in a concave surface. In the final stage, the bucket comes to an abrupt stop, while the water continues to spin and its surface remains concave until the rotation stops. Comparing the first and third stages of the experiment, we can see that in both cases the relative motion of the water and the bucket is the same. The water rotates relative to the bucket or the bucket relative to the water, which is the same. However, there is clearly an observational difference between the two situations. In one case the surface of the water is flat, and in the other it is concave. Newton concluded that only in one of the two situations the water really rotates, and in the other it really, i.e. absolutely, rests. The criterion of absolute rotation is, of course, the occurrence of apparent forces, in this case the centrifugal force, which changes the shape of the water's surface. Relative to what does true rotational motion occur? Newton had no doubt that the only possible answer to this question is, relative to absolute space. The water molecules participating in the motion change their position in relation to absolute places in space, and this absolute, not relative, movement of water manifests itself in a real physical effect. However, Newton was aware that not every type of motion has observable effects. Uniform motion, as Galileo had already noted, does not produce a deformation of the moving body. Why does absolute space manifest itself only when the body accelerates relative to it, and not when it simply changes its position? This question remains unanswered. Consequently, for fundamental reasons, we cannot empirically verify the existence and identity of absolute positions in space. We assert that the accelerating body must change its position in absolute space, but we do not know from where to where. It may be that a given molecule of water in a bucket moves absolutely from point A to point B on the circumference of a circle, but this motion may also be combined with an unobservable uniform motion of the entire universe at an incredible speed in one direction, and thus the absolute position of the particle under consideration after a second may be many thousands of kilometers away. But we have to rule out the possibility, if we accept Newton's point of view, that a particle of a spinning water sample could be in the same absolute place all the time. The presence of apparent forces does not give us an unambiguous criterion for identifying absolute places, but the assumption of the existence of these places is the best explanation for the observable behavior of bodies subjected to acceleration. However, the assumption that the existence of absolute space is the only, or, more cautiously, the best, possible explanation for inertial effects has been challenged. Ernst Mach, an Austrian physicist and philosopher of the late 19th century, noted that Newton completely ignored the existence of bodies other than the bucket and the water, as if the bucket of water was the only thing in the universe. However, this is not the case. The bucket and the water are spinning relative to the rest of the universe. The first and third stages of the bucket experiment differ kinematically. In the first, it is the bucket, not the water, that rotates relative to the Earth, the Sun, and the fixed stars. In the third, the bucket rests and the water begins to swirl in relation to the surroundings. In order to obtain the full symmetry necessary to derive Newton's conclusion, the following two situations should be compared, one in which the water is spinning relative to the bucket and the rest of the universe, and the other in which the water is resting and the bucket and the entire universe are turning around it. However, this is impossible for obvious reasons. We cannot rotate the entire universe. Mach's argument against Newton's conception of absolute space can be understood in two ways. In the weaker interpretation, Mach simply shows a gap in Newton's reasoning that blocks the way to its conclusion. However, many commentators interpret Mach as authoritatively stating that the rotation of the entire universe relative to the water would have exactly the same effect as the rotation of water itself. A centrifugal force would have occurred to change the shape of the surface of the water. Mach himself was quite cautious in formulating what-if hypotheses, however his name is associated with a specific doctrine. This doctrine, known as Mach's principle, states that inertial effects must be explained by the physical influence of the entire universe on a given object. In particular, inertial mass is the result of the influence of the rest of the universe on each body. A solitary body in an empty universe would not have any inertial properties. For obvious reasons, this is speculation that we cannot directly verify. Mach's ideas had a great influence on the young Albert Einstein in his first attempts to create a general theory of relativity, in which there would be no room for absolute space, and all motions without exception would be relative. A staunch opponent of the absolutist concept of time and space was Gottfried Leibniz, a German polymath. He found it absurd that space could exist without the objects that fill it. Geometric relationships, such as distance, occur primarily between physical bodies, and only derivatively between spatial points. Spatial and temporal points and places owe their identity and existence to the objects and events located in them. Leibniz's conception of space and time is called relationalism, as it emphasizes the relational nature of the temporal and spatial properties of objects. It makes sense to say that body A at some moment is 100 meters away from the body B, but it cannot be assumed that body A is absolutely located at a certain place, 100 meters away from the location of the body B. Leibniz formulated a famous argument against the absolutist concept of space, known as the shift argument. Let us assume, as the absolutists would have it, that space exists objectively and independently of the physical objects that occupy it. In such a situation, one can consider moving all material bodies in the universe in a certain direction by a constant distance, for instance 5 meters, without changing their relative positions. The situations before and after the shift would be different, because the objects would occupy numerically different places in them. But this difference would in no way reveal itself empirically or qualitatively. Two states of affairs, differing only in the position of the whole world with respect to absolute space, would be an example of pure numerical difference without any difference in qualitative properties. Leibniz was a supporter, and de facto the author, of the metaphysical principle of the identity of indiscernibles. It states that absolute qualitative indiscernibility, by means of properties, implies identity, being the same object, or, in a logically equivalent form, that every two numerically different objects or states of affairs must differ by at least one property. Leibniz justified his principle by referring to an even more abstract metaphysical rule, which he called the principle of sufficient reason. Putting this principle in theological terms, we can say that God, when taking any action, always has a rational reason to choose one of many possible options. According to absolutists, God first created space and time, and then placed the physical world in them. The problem is that the Creator could have no reason to choose one of the infinitely many possible locations of the physical world, and thus the principle of sufficient reason would have been broken. The solution to this theological and metaphysical problem, according to Leibniz, was the assumption that it was only the creation of the world with the space-time relations between its elements that allowed time and space to exist as secondary entities. For naturalistically oriented philosophers, the principle of the identity of indiscernibles may have a more empirical justification. Assuming that only qualitative facts based on the possession of certain properties can be empirically available to us, we must conclude that purely numerical differences, based on numerical individuality, cannot be subjected to empirical verification. When it comes to the location of the entire world in absolute space, it is clear that we cannot distinguish between the available options. Facts about the absolute spatial location of the world, as well as the location in absolute time, have no empirical consequences, and therefore can be treated by us as unnecessary baggage. Leibniz, a rationalist philosopher, would not be satisfied with such an argument, but the principle of the identity of indiscernibles is usually justified in this way by contemporary philosophers of science educated in the spirit of logical empiricism. Leibniz's shift argument is widely regarded as an extremely serious challenge to absolutism with respect to time and space, which balances and even outweighs Newton's argument from the presence of apparent forces. Ultimately, however, the dispute between absolutism and relationalism does not find an unambiguous solution on the basis of classical mechanics. In the following parts of the book, we will see how this dispute developed with the arrival of more recent theories of time and space, special and general relativity. There will be completely new approaches and arguments, such as a modern version of Leibniz's shift argument, known as the whole argument. Despite the considerable technical advancement of the new arguments, the debate between the two positions is still ongoing, and its resolution is as distant as in the times of Newton and Leibniz.